Welcome to Okonkwo Academy. In this tutorial, we'll be going through the classification of differential equation. As usual, please do not forget to like, comment, and share this video to your friends. If you are new to our channel, please subscribe and turn on the notification button so that you can get all videos or all the notifications on our videos. In today's tutorial, we are going to discuss the four types of classifications of differential equations. The first one is known as the type. In the type, we have the ordinary differential equation and the partial differential equation. With the ordinary differential equation, the derivative of the unknown function, that is the dependent variable y, depends on a single variable, in our case x, and it is denoted by dy dx. For the other type, which is the partial derivative, one dependent variable can be dependent on several independent variables, and it is denoted by the change in y over the change in x. In this case, the other dependent variables are normally held constant, so you can get something like change in y over change in x while holding z constant, or change in y over change in z while holding x constant. So that is it for the type. When we come to the order, when we say the order of a differential equation, it is the highest derivative that appears in the equation. Let's take our example 2 for example. In our example 2, we have d squared y over dx squared plus 3k multiplying dy dx plus y equal to 0. Our y is our dependent variable, and it has its first derivative, which is dy dx, and the derivative of this derivative, which is d squared y over dx squared. The order here is the highest derivative in this equation, in our case this. So d squared y over dx squared becomes the highest order in the equation. So this equation will be known as a second order differential equation. Assuming this place was d cubed y over dx cubed, then this equation now becomes a third order differential equation. The next type is the degree. When we come to the degree of a differential equation is known as the power or the index of the highest ordered derivative. What do we mean by that? Let's take this example. Example 3. We have d cubed y over the x cubed all exponent 2 equal to d squared y over the x squared all exponent 5 plus 2. Now we have two derivatives here, that is d cubed y over the x cubed and then d squared y over the x squared. In this equation, the highest order is 3, but we realized the power of the highest order here is 2, but the power of this one here is 5. But that doesn't make the degree of this equation 5, because we've already established that the degree of the equation here is 3 because of the cubed y over the x cubed. Therefore, sorry, we've established the order here is the cubed y over the x cubed. Hence, our degree here becomes 2. So our degree is always dependent on the highest order in the equation. So this equation here becomes a third order differential equation of degree 2. If here was supposed to be a 3 or even a 4, it will still be a third order differential equation of degree 3 or of degree 4. It doesn't matter whether the power here is larger than this one. So far as this here makes this equation a third ordered equation, the degree is always dependent on the highest order here. The last classification we have here is linearity. For a differential equation to be linear, it has to satisfy 3 conditions. The first condition is that the dependent variable and all its derivatives only occur to the first power. By this point, we now understand that a dependent variable, if we have dy dx, the dependent variable is always the one at the numerator side, that is the y. And then the independent variable is at the denominator side. The unknown function that is dependent on the other variables is always found at the top. And then the independent one is at the bottom. So in our case, y, if we take this example 4, dy dx plus y equal to x squared. Y here becomes our dependent variable and x is our independent variable. We understand that. So we said the first condition is that the dependent variable and all its derivatives. So the dependent variable here is y, and dy dx is a derivative of y. The squared y over the x squared is a derivative of y. The cubed y, d to the power 4, d to the power 5, they are all derivatives of y. So all these derivatives of y should have a first power or a degree of 1. So you might see in other books that the dependent variable and all its derivatives must occur at a degree 1. It doesn't matter, it still means it should occur at a first power. So if we take this example, we realize that y here is raised to the power 1. That is why we don't write anything here. Dy dx is raised to the power 1. That is why we don't write anything here. So that is what makes, this is the first condition you need to satisfy in order to become a linear equation. But that is not all. You can't base on one condition to make an equation a linear equation. The second condition is that there should be no terms or no products of the dependent variable and its derivative in the equation. What do I mean by that? Assuming we have dy dx then multiplying y in an equation. Another way we can write dy dx is also y prime. Y prime here is different from y exponent 1. So if you see y prime in any book at all, it also means dy dx. It also means dy dx. So the short form for writing dy dx can also be y prime. If you want to write d squared y over dx squared, it is y prime prime. So instead of writing dy over dx or d squared y over dx squared, we can simply write it as y prime or y prime prime respectively. So with the product, I want to rewrite this product here. So with the product, let's say we have y multiplying y prime. So we've now established that y prime here means y means what? Dy dx, right? So if you have any equation, if there's any equation that has this here, a product of the dependent variable and its derivative in any part of the equation, whether the left hand side or the right hand side, it does not make it a linear equation, or it doesn't satisfy the conditions to become a linear equation. So if we take this example, for instance, these two terms, this is one term, the derivative of our dependent variable, and this is our dependent variable. It is separated by a plus sign. That is okay for us, because if it were to be a multiplication sign, meaning it is a product, and hence this equation here cannot be a linear equation. So our example 4 has satisfied two of the conditions to become a linear equation. Let's take the last condition. The last condition is that there shouldn't be any trigonometric, logarithmic, or exponential form of the dependent variable and its derivative. What do I mean by that? For our trigonometric signs, we know of the sine, we know of cosine, and we know of tangent. For logarithmic, we have log, whether to the base 10 or to the base 1, 2, or natural log at all. And then the exponential, sometimes we might see e exponent 2. Yes, so if we have any of these ones are the trigonometric ones. This is the log, and this is exponential form. If any of these functions are attached, or any of these are attached to the dependent variable or any of its derivatives, something like sine y, it doesn't satisfy it being a linear differential equation. So let's take our example 5 and see. We have dy dx squared plus cos y equal to 1. This equation does not satisfy to be a linear equation. Why? Because first of all, although we have dy dx here, our first condition states that it should be the dependent variable and all its derivatives should occur at a degree of 1. And here we have a degree of 2. So this doesn't make it a linear equation. This term here doesn't allow this whole equation to be a linear equation. If we take the next term too, we have cos y, cosine of y. And our third condition makes us understand that there shouldn't be any function of the dependent variable and its derivatives which will be in the trigonometric form, log, or exponential form. Hence, because of these two terms, this equation does not satisfy to be a linear equation. Hope we understood everything that we've said here. If there's any problem that you'd need help solving, you can kindly comment it so that we can help you. Once again, thank you very much for watching this video. I'll see you in the next one.